Hi there, Physics 131. Here's the short pre-class reading video for class 23, in which we're starting chapter 18, extended bodies at rest. These are basically static equilibrium problems. It opens up with a picture. It doesn't actually say who this is, but I think this is Sarah Robles, who's a weightlifter. Actually, she's won some Olympic medals in the last couple of Olympics. This is an older picture. So she actually got into trouble long ago for steroid use, but she cleaned up her act since then. And I think these wristbands she wears is because she does get a lot of pain in her wrists, and they talk about health pain or back pain here. But basically, when you're weightlifting, you have to hold something static, and there's torque as well as force that has to get taken into account. But I'd like you to read through the first two sections. The first one is just sort of defining some variables. It's called extended and rigid bodies. Basically, they're saying that we're no longer using the point-like model of an object in this section. So a rigid body is a model of a real extended object. When we model an extended object, we assume the object has a non-zero size, but the distances between all the parts of the object remains the same. So you can, I guess, rotate the object or accelerate it, but it doesn't change its shape very much. So they talk about center of mass. So she first starts, it's weird, talking about pushing pieces of cardboard around or pushing these little heart shapes or something. But basically, there's an idea that at the center of an object, there's something called the center of mass, and there's a qualitative definition. Center of mass is a point where a force pointing directly toward or away from that point will not cause the object to turn. And so the gravitational force acts as if it's sort of pulling on the center of mass. So that's going to be important when we're getting to the next section on torque. Okay, section 8.2 on torque. So when an object turns around an axis, physicists say that it undergoes rotational motion. The axis may be a fixed physical axis, such as a hinge on a door, or the axis on a wheel, or it may not. It just might be, for example, the Earth rotates around an axis which joins the North and South Pole, but that's not a physical thing. So talk about doors. So basically, when you open a door, it rotates around its axis of rotation, and you have to apply a force to the door to get it to rotate. So it turns out that the ability of a force to rotate something or cause rotation is coming from torque. And there's a lot of examples of how you get to it. I'll come back to that in a second. Where is it here? Somewhere here they give you an actual equation for your aid sheet about torque. There's a lot of beating around the bush. They're trying to motivate things in this book, right? So that these equations don't seem to come out of nowhere. But basically, there it is. Equation 8.1. Tau, which is the torque, it's a Greek letter, is plus or minus, I guess depending on if it's going clockwise or counterclockwise, F L sine theta. F is the magnitude of the force. L is the magnitude of the distance between the point where the force is exerted on an object and the axis of rotation. And theta is the angle the force makes relative to a line connecting the axis of rotation to the point where the force is exerted. And it says see figure 8.10. So here's a method to determine the torque. You've got an axis of rotation. Here is L, the distance between the axis of rotation and where you apply this force. So you want to find the torque from this rope where it's attached to this beam. Well, you take the T and you multiply times the L times the sine theta. And you get a torque in units of newtons per meter. So definitely read through that and some of the examples. Just scrolling back up a little bit, there was an idea I zoomed past about static equilibrium. An object is said to be in static equilibrium when it remains at rest. So it does not undergo acceleration either that's translational or any rotational acceleration. So really what you're doing in this whole chapter is you're still balancing forces to keep something in equilibrium. So you balance the y components of the forces equals 0, balance the x components of the forces. Now you're also going to balance the torques. So all the clockwise torques have to get balanced by counterclockwise torques. And that's the basic gist of today's reading. But I very much encourage you to actually do the reading and look through the examples before coming to class. All right, thanks. Bye.